Hey everybody, welcome to Super Coding Fun Time with me, Eugene. Hey everybody. This is our, good lord, and I've already messed this up. This is my second stream, and this week I have a guest with me,
Hi.
Professor Jay Foley. Jay Foley's a quantum chemist just like me. He got his bachelor's degree from Georgia Tech in 2006, and then he went on to do a PhD at the University of Chicago in David Mazziotti's group, which is the same group I was in.
It was.
It was. I got my PhD in 2009, and then he got his in 2012.
Yes.
And then he went on to do a postdoc at Argonne National Laboratory.
That's where you did yours.
Which is where I did my postdoc. Exactly, with the same postdoc advisor, Dr. Stephen Gray. So at Chicago, Jay did research on reduced density matrix methods, and you did some time domain work as well, right?
Kind of. I kind of did. I can say more about what
yes, that'll make more sense at that time.
If anybody cares.
Somebody will care. Somebody will care. Anyway, he stayed at Argonne for a few years, and then he started his independent research career. Yes, big money research VC cares. Thanks so much for caring.
Okay.
Anyway, he started his independent research career at William Patterson University in State University of New Jersey, which is another crazy coincidence. I grew up in a town called Verona in New Jersey, and that's where Jay lives now. So he's trying to replace me. I have no idea why. It hasn't worked yet.
It's actually, this all comes back to Twin Peaks.
It is Twin Peaks Day.
Today is Twin Peaks Day, everybody. So it's February 24th. That's the day that Agent Dale Cooper arrived in Twin Peaks in, I think, 1990. So that might be before some of you were born, but it's not before me and Eugene were born because
we're old.
We are not Gen Zers. We are millennials.
I am technically a millennial, like the oldest possible millennial.
Yeah, I'm only a couple years younger than you, so I'm a millennial too. Anyway,
Lactase TV.
There was a Twin Peaks connection there too, though.
I don't know what in the world that is, but thank you.
That's enough to say. I guess I'll stop.
I think this means that we are old because I don't know what that means. So cool. Okay. Anyway, Jay's been at William Patterson since 2019. He's doing great. Super successful young faculty member there. Did I say it wrong? I can see through my face for some reason. Anyway, Jay, if I didn't introduce you well enough, you can say whatever you want about yourself and tell us a little bit about what you're going to be programming today.
Yeah, absolutely. I think I'm going to, first of all, seems like my screen went away again, but hopefully it's back now. So what we're going to do today is we're going to code up a quantum dynamics method called the split operator method. And this is, I don't think anybody can see my screen.
Nope, it's green.
Yeah.
Okay. Hey, so everybody, this is the first glitch I have Jay's face through Zoom and his screen and audio through Discord. And Discord seems to be acting up, or Jay doesn't know how to use it. It's one of those two things.
I think we're back now. I'm pretty sure. Yeah, I think we're back now.
Shoot and smile. I think these people must come from my class.
Wonderful.
Thanks for coming, guys or girls.
You can see now my screen. So let me tell you a little bit about what we're going to do. So we're going to solve the time-dependent Schrodinger equation that's here. So this is kind of like, the Newton's law for quantum particles. So this is, given we've got a quantum particle somewhere, and we know something about it, meaning we know its wave function. When it starts out, then this equation tells us how it changes in time.
How what changes?
How the wave function changes, which is what really describes the electron. Basically what it tells you have on the left-hand side, you say, how does the wave function change in time? And on the right-hand side, you say, well, it changes However, this H hat, which is called the Hamiltonian operator, however, that H hat changes the wave function. So on the right-hand side, you've got this operator called the Hamiltonian operator, which is also called the energy operator. So that thing actually does some operation on the wave function and results in a new function. And so that new function, what that results from H hat on the wave function, encodes how the wave function is supposed to change in time. Basically, the velocity of the wave function is equal to H hat acting
Velocity
on.
of the wave function.
Yes. It's time rate of change. Yeah.
It's time rate of change. Hey, thanks, Water the Cow, for the follow. Cool. This means my setup hasn't crashed yet.
Yeah, it hasn't. So what's the Hamiltonian? It's got kinetic energy. This is how we write kinetic energy in quantum mechanics. It's a little different than in classical mechanics, right? Classical mechanics, kinetic energy is velocity squared divided by 2m. In quantum mechanics, it's kind of appears to be something
Smile.
like...
Thanks for the follow. I think you meant to say momentum squared over 2m.
Yeah, I did. But also, velocity squared times m over 2 is the same thing. Right?
Yeah, it's the same thing.
Thank you.
I remember, I'm going to interrupt Jay a lot because I'm obnoxious. I remember I went and gave a seminar. I gave a seminar at William Patterson, and one of his colleagues interrupted me and corrected like basically every slide that I had. I hope they're not watching.
I'm sure they're not. I
think I messed up my kinetic energy operator, actually.
Did he ask you about the kinetic energy operator?
Yeah, and he asked me about a vector potential as well.
Yes. Okay.
Sorry, Jay. Continue.
So one thing is that we have an operator for the kinetic energy. So this operator, right, it's got a derivative in here. It's actually got two derivatives. So this thing is going to take two derivatives of our wave function and then multiply the result by these constants. The potential is actually a lot simpler. The potential is just going to multiply the wave function. And one of the things that we're going to do as we go along, hopefully, is we're going to define different potentials, and we're going to shoot our electrons at those different potentials and see how they behave differently. There's one thing that electrons can do that classical particles can't do is they can tunnel through potentials. That means even though they don't appear to have enough energy to, let's say, surmount a hill, they can still do it, at least with some probability. And so you can actually see that in the simulations that we'll run. So there's a whole bunch of different ways to solve this equation. Basically, you can more or less, well, yeah, if you're comfortable thinking about these differential equations, you can see that this is just a first order differential equation in time, and that would lead you to say, aha, solving this differential equation in time, really the result is going to have this kind of exponential form, right? There's going to be an exponential of these constants on the right-hand side, so negative I over h bar, and this operator, right, acting on the wave function. So that's cool, and you can certainly exponentiate an operator, and you can definitely exponentiate an operator, a matrix representation of an operator, which is what we're going to do implicitly. But it's much easier to do that if that matrix representation is diagonal. And the way that this kinetic energy operator works, it's not really a diagonal operator in real space. So the derivative, right, if you can think of like what a derivative does, is it takes differences like if you take the derivative of a function at some point, right, it's got to know like what's the function doing like a little bit ahead of the point and a little bit behind the point. So it's kind of clearly not exactly this local thing, which only cares about the point itself, right? It cares about things forward and backwards. So its matrix representation is not diagonal. Um, it turns out, though, that the Fourier transform of the second derivative operator looks like a quadratic function. So, in fact, it is a quadratic function. So, what's the Fourier transform of the kinetic energy operator? It's really p squared over 2m.
Wow,
Eugene
just
already,
like the classical version.
that's right. Eugene already commented on this. And so if you have your wave function evaluated not in real space, but in this momentum space, then the kinetic energy operator is no longer a derivative. It's actually just your p variable squared divided by this constant, 2m. So the whole idea of the split operator method is really to break up.
Could you scroll up? Oh, well, never mind. If you're going to go up, that's fine. It's just some of the words were behind my head that were relevant to what you were talking about.
Yeah. Okay, sorry. So you want to break up this time evolution operator, which is really the thing that maps your wave function from one instant in time, t, to a short period of time later, t plus delta t. So you can first break it up into these products of three different exponentials. So exponential with the potential, multiplied by an exponential in the kinetic energy, multiplied by an exponential in the potential.
Hey, I have a really naive question because I don't ever use these types of methods. Doesn't that mean those operators have to commute to be able to break it up that way?
Yeah, they don't. Yeah, so this is a really good question. Technically, they do need to commute for this to be exact. So one of the things that is a criteria is that your time step is very small. So this part of the Hamiltonian that doesn't, the parts of the operators that don't commute contributes an error, which is evidently third order in the time step.
Evidently, it's obvious just from looking at it, don't you? Wouldn't you say?
So this might be a good time for me to, let me change how I'm sharing my screen for just a minute. This might be a good time for me to point everybody
Ladies and gentlemen, that's the stream.
Are we back?
Yeah, but now I have to put you back in full screen. It's fine. Vigorous applause!
Sorry about that.
Big money research VC can appreciate some quality free entertainment.
Let me know when we're ready to proceed.
This is exciting. Big money research VC might fund us, Jay.
Yeah, I hope
that's
so.
possible?
It sounds like you've got a lot of big money and some venture capital.
It could be an NSF program manager.
Oh my gosh. So let me at this point in time to address, this is a good segue, Eugene. So first I want to acknowledge.
I can't help but get excited when we're talking about big money.
So I want to first acknowledge that I'm going to show you an implementation which is based on one that a former student of mine, Jason, did. So Jason's awesome. He's now a medical student at University of Miami. I
didn't know that. That's great.
Yeah, that's awesome. So I linked a little story about him from when he was at William Patterson. So here's Jason looking very smart in front of some theory. And he got this implementation from a really cool project called the Arcane Algorithm Archive, which has a really good explanation of the split operator method. I also linked to a really good paper on the split operator method that does discuss things like these errors. So
when you say linked, what are you talking about? In your
I'm
Jupyter
talking
thing?
about in my notebook.
So Jay has this Jupyter notebook. This is on GitHub already?
Yes.
Is it on your? Yeah. Okay. Cool.
It's on my GitHub in a repository called Quantum Twitch. So
I will try to find it and put it in the chat because everybody wants to play with it.
Yeah, I think so.
Oh yeah, you added me to this and I never joined. Sorry.
Mm-hmm. So let me change how I'm sharing my screen one more time. Stop streaming, change windows. Okay, let's just stick here. But yeah, you're absolutely right, Eugene. So this expression implies that k hat and v hat commute, which they don't, but it's okay. The truncating the non-commuting terms contributes an error, which is proportional to the time step to the third power. So we're going to make this time step relatively small.
Did you mean to make the background green?
No. What is going on?
You're killing me, Jay.
It doesn't look green to me. It looks like, yeah.
Oh,
Now
there we go. Apparently it's a problem on my end. You're killing me, Eugene. Jay, I don't want to make you nervous, but there are 18 people watching you right now.
That's awesome.
Okay, so I'm sorry I interrupted about the commutator. I thought if any of my students were here, they would be excited to hear a word that they hear in class.
So we're going to ignore the non-commutating terms.
Nice.
And the other thing that we're going to do, is we're going to transform the kinetic energy operator into momentum space.
Hold on, I'm sorry, Jay. Giorgio, thank you for the follow. GG. I promise I'll stop interrupting you.
No worries. So we're going to Fourier transform the kinetic energy operator. That really means that we're just going to build an operator which looks like p squared over 2m exponentiated. And the other thing that we're going to do is when we apply that operator to the wave function, we need to actually Fourier transform the wave function as well. And then once we've done this operation, we can inverse Fourier transform back to space. So basically, we're gonna the kind of price for this more friendly operator is the fact that we're going to have to carry around two wave functions. One wave function will be in real space, and one wave function will be in momentum space. And hopefully we'll get to a point where we actually have enough time to plot movies of the momentum space wave function too.
We've got plenty of time.
So that would be fun. Yeah, I guess we do.
Thanks, so JuiceMan01 for the follow. Oh, I thought I could say it while Jay wasn't talking.
I'll never not be talking. So we'll have two grids as well. We're going to have a real space grid. And these are how we're going to define the points on the real space grid. So grid point x sub j is just going to be whatever x min is. Probably it'll be 0. Plus the integer j times delta x, where delta x is going to be whatever the maximum grid value is, probably 500 minus 0, which is x min, divided by the number of grid points minus 1. So that's how we'll define delta.
Did you say x min?
X min. Yeah. Yes.
Cool.
And then we'll have a momentum grid, right? Where grid point p sub j is going to be the integer j times 2 pi times Planck's constant, or h bar, divided by the number of grid points times delta x. And one thing that's important to note, so our j for the real space grid is going to go from 0 to n minus 1. And our j in the momentum space grid is going to go from negative n over 2 to positive n over 2, and it's going to include 0. So we're going to make sure that we're going to have basically left and right moving momentum components represented. That's important. Okay, so if you have any questions, chat Eugene and he's going to explain them. This is an outline.
I'm sure I'll explain it really well. Can I just make sure I understand? So you're going to... Part of this problem is hard to do in real space. So you're going to hop back and forth between real space, and which means like x, and momentum space. So it's like a leapfrogging thing between these two spaces.
Yeah, exactly.
Okay.
And it's going to actually be really easy because we can, in Python, if you want to do a Fourier transform, you just type np.fft.fft. And that's it.
Mustafanajad on the Sina has a question. Why does the momentum grid have this form?
Oh, yeah. So, well, one thing is that, right, the momentum is reciprocal to the position. So, so our momentum spacing is going to be inverse to the position spacing. Why do you, so your other question is why is it gonna go from negative n over 2 to positive n over 2? And I think that's gonna
Thanks for the
be
follow.
because we're gonna have maximum components that can be positive or negative. Hopefully that answered your question. Sina, did I answer your question?
Well, we have to wait 6 seconds because of the delay to see if you answered his question.
If I didn't answer your question, we can.
We've already moved on. It's too late.
Yeah.
Just kidding.
Okay. So here's like an outline, and I'm going to kind of keep toggling back and forth to this outline. But there's just basically a handful of steps. So I have like a basic class, I think it's called quantum outlined, and we're going to add attributes to it for like our spatial grid and our momentum grid, and we're going to add some parameters that we'll need for our simulation. We have to initialize our wave function somehow. I picked this Gaussian wave packet. I love Gaussian wave packets.
My students don't know what that means. So can you explain it?
I will, absolutely. So we'll get to, so hopefully we'll get really familiar with what it looks like very soon. But basically, the Gaussian wave packet looks like a bell curve, and it looks like a bell curve both in real space and in momentum space, right? So in real space, it's centered at a particular position, which I'll call x naught. And I guess, we can pick any value of x naught that we want, but maybe we should put it kind of in the middle of our box. So at x max over 2, that would be, a good way to do it. And then basically, that's the peak of the bell curve. And then it, comes down in that nice bell shape and is symmetric on either side and has a width, which is related to this sigma parameter. And we can define sigma any way we like, but maybe I think I played around with it and sort of taking the range of x values divided by 30 gives you kind of a nice value of sigma. So you get a packet which is fairly well localized. It's not like spread out over the entire grid. It's also not like really sharp and pointy.
So
in real space, yeah, go ahead.
I thought you were done. I was going to ask if I could add to that.
Oh, you absolutely can.
So you guys can see my mouse, I think. Who knows? That exponential term, e to the ikx, that's a pure momentum function. So if you think of that thing alone, that means your particle has a specific momentum, but you have literally no idea where it is. So that's what this Gaussian envelope, you tack that onto your pure momentum function so that you still have something that's oscillating with the right frequency for that momentum function, but it's localized in space instead of being spread out over all space. That's right.
So that means that even though this piece alone, the plane wave that Eugene was talking about it is a momentum eigenfunction. It has a precise value of momentum, but the Gaussian envelope ruins that precision because it localizes it in space.
And it ruins the precision and exactly what you said. So that's why I interrupted to say the same thing.
But this is also a special wave function because it's a minimum uncertainty wave function, right? You cannot do better in your delta P, delta X than the Gaussian wave packet.
Hey, Jay, can you do me a favor? There you go. Can you stay right there?
No.
So you don't leave the screen?
Absolutely not.
See if I invite you back.
So there we go. But we'll make sure that we plot this too. So
fun.
All right. Okay, we got to define v hat, and that's where we can get some audience participation. So v hat could be nothing, right? Free particle. Could be a square barrier, could be a square well, could be a Gaussian barrier, could be a harmonic well, could be something else. We'll define our K sub P.
Are you going to explore all of these potential forms, or are you just going to pick a couple? I want to see them all.
Let's see what we have time for.
All right.
We'll try to make it flexible so that we can redefine the potential very easily. Right. So we got to define these V hat and K hat operators. And then once we have them, we can exponentiate them. And then we got to write our code for our split operator method. So this is kind of the schematic of how it looks like. So there's like a partial update to the wave function from the V operator, right? Fourier transform that result. Another partial update in momentum space from the K operator. Inverse Fourier transform, then final partial update from the V operator, and that yields your updated wave function.
Cool.
So that's where we are. So I guess I'm gonna start writing some code now.
You're doing this all in Python. That's exciting.
This is all in Python, yeah. Yeah. Okay. So here's like my base class, and we're gonna add more to that. I also have most of the animation written because I never remember how to animate, but everything else we're gonna write. So wish me luck.
Last week, I had my makefile written already because I have no idea how to write a makefile. I don't think anyone knows how to write a makefile.
That's a good strategy. Okay, so what else should we have? So we need xmin. And so, by the way, I'm just going to assume that we're going to pass a Python dictionary, which is going to contain some of these keywords, maybe all of them. And so this is something that is really handy about Python, is you can just easily parse these dictionaries for their values, like so.
It's almost cheating.
I know.
You know, shoot and smile. I love Python too, but I don't know enough about it. I do everything in C and C++, and it's way more difficult
Yes.
than this.
So, by the way, so what we've done now, we've added two parameters, xmin and xmax, and we've given them default values as well. So if at the time that we want to start our simulation, if we actually bother to specify what xmin and xmax are, that's great. But if we forget, xmax will be 500 and xmin will be 0. Okay. So if I remember correctly, then that should also give us, we should have a formula for dx based on what xmin and xmax are. So let me scroll up and make sure I remember. So dx is xmax minus xmin divided by n minus 1. So that seems like another parameter that we need. What is n? So maybe we'll think to call that grid points as a parameter. So let's say if grid points in args self dot in grid points is equal to args grid points.
Nice.
Else, I don't know. If the default number, if the default xmax is 500, maybe we should
501.
Say it again.
501.
501. Okay, fair enough. I like that. Okay. So now we should have all of those parameters that we need to calculate delta x. So let's just calculate delta.
Very cool. Lactase TV is trying to learn Python right now. So hopefully you can explain some of the more complicated things you're doing. Can you scroll up a little bit? I've tried scooting myself off the screen and I'm going to fall out of my chair soon.
Yeah, absolutely. I'm sorry about that.
So delta x is just the difference between xmin and xmax. Perfect.
Awesome. I'm going to hit play, make sure I haven't already.
What is self? Self is like The instance of the class that you're in.
That's right. Yeah.
So
So
even when you so if you're inside a class in C and C++, you don't have to refer to yourself in that way. Do you always have
yeah,
to do that in Python? In every class function you have to do that? Or just in
I
this
believe
initializer thing?
no, yes, and all functions. Yeah.
Hmm.
And all the functions where you want to use either methods of your class, which would be self dot method name, or attribute, or whatever you call it, attributes of your class,
I
which
guess
would be
that's
self.
fine. It makes it clear that it's something from your class.
Yes, exactly. Exactly. Okay, cool. So we're here. We have this done.
Halfway
So we
there.
need to halfway there. So we have to define our momentum grid. Oh, Eugene, you already kind of hosed me.
Oh, I'm sorry.
The spatial grid points needs to be an even number. So let's put a little check in
Why does it
here.
have to be an even number? I don't believe you.
Uh, J, which is an integer, has to be between negative n over 2 and positive n over 2.
That's just like your convention.
That is just like my convention. I think it's going to be better, though. Let's make sure it's even. So let's see.
So in the
Yeah.
chat, Sina's saying that the fact that you have to refer to self is because it's an interpreted language, not a compiled language. So you have to be clear about which memory address you're talking about. I believe you.
So this is my. There's probably a way to ask if a number is even in Python, but
It probably does a mod under the hood.
it probably does.
Jay, do something crazy. We lost a few viewers. Thank you, Shoot and Smile, for sticking around. He's a long hauler. Or she.
Yes, definitely. Okay, so now there we are. So we got our delta x, okay? So now we got to make our momentum grid.
They are missing out on this prime investment.
Yeah. Oh, did Big Money VC leave?
No, they're still here.
Oh, good. Okay.
We got them on the hook. Just got to reel them in.
Yeah. So let me think about this. This is. So first I can do my self.dp, right? So what is the grid spacing and momentum space? I'm sorry, everybody, for toggling back and forth like this so much. This is the grid spacing, 2 times pi times h bar divided by n times delta x. I think that's right. Yes. Okay. And we should also, I guess, define h bar before we do this.
It's 1.
Hey, what's h bar?
1.
H bar is 1. Good.
What's the speed of light?
Oh, I don't know.
Anyone from my class know what the speed of light is in atomic units? Oh, you're so close. 127.
127?
It's 127.
Awesome.
Oh, you're not from class? Okay. Why would a big money research CV need to take PChem 2? They wouldn't. Can you scroll up a little bit?
Yeah.
Hey, Jay, do you want to plug your podcast?
Oh, I do. Yeah. So I didn't say that I really like light and matter. That's part of why I'm doing this. But I have a light matter themed podcast with my good friend Dugan Hayes, who's an assistant professor at University of Rhode Island. And that podcast is called the Geppert-Mayer Gauge, named after Maria Geppert-Mayer, who won the Nobel Prize for her work developing the nuclear shell model, but she was also the first person to predict two-photon absorption. So she has significant importance in nuclear physics, but also in AMO physics and nonlinear optics.
Another mutual friend of Jay and I, Greg. I can look it up and put it in the chat. Greg and I were just talking about two-photon absorption.
Oh yeah?
He was looking. One of his colleagues wants him to calculate something. I'm going to get everybody to follow you on Twitter too. Because why not?
Yeah, why not?
Free clout. I've got all the clout. I'm just throwing it out here. And I'm sure I can find one of your podcasts on your Twitter timeline, right?
Oh, yes. Absolutely.
I'll just send the link to Spotify. Is that good?
Yeah, that's good.
It is a long one.
Okay. So now we have dx, we have xmax, xmin, and what else do we need? We need the x grid, of course.
Now, who's your favorite X-Man?
I don't even know any of the X-Men.
Calm down, Bronco! Wow, what a day. Thanks for watching. We're doing chemistry, believe it or not. I think you're in Ken's Gen Chem class, is that right? Or you were? Or am I mixing up people? I don't want to reveal your secret identity, so maybe I shouldn't press.
Okay. So, all right, let's go ahead and before we get in too deep, I'm just going to try to create an instance of this class and make sure that the grid looks okay.
Can you scroll up a little bit?
Yeah, I sure can.
So the reason I asked that question was just because I want to convince you that, believe it or not, what we're doing is chemistry. It's just quantum chemistry. I guess it's quantum physics, but close enough.
And do I need anything else? Nope, I don't need anything else. And equals quantum.
What do you use to plot?
I'm going to use Matplotlib.
Matplotlib.
Yes.
You know, I gave an assignment in my graduate course that used Matplotlib, and I'm pretty sure I learned every piece of Matplotlib code from one of your Jupyter notebooks.
Okay, so here's
a bunch of numbers.
Notice
that they would be nice even integers if your number of grid points was 501.
I know. Uh-oh. Something's not working with our Xmax.
Why?
Because I said Xmax is X_max. That's why.
See, this is a problem with Python.
There we go. Okay, cool. This looks good. So That's our spatial grid. Let's check our momentum grid. Okay, good, I think.
No. Where's positive 5?
Where is positive 5?
I do not think that is right.
I don't think that's right either. I have to confess this very funny way of doing things.
Jay, do you still run?
Oh, I do.
How many miles do you run a week?
That's a great question.
Thank you.
Here we go. I think now I'm right.
That looks much better.
You dodge this question. Less than 40.
Holy
but
cow.
Hopefully more than 30.
That's wild. I am stoked that I have run 10 miles so far this week.
All right, that's not bad.
Do you run every day?
I do pretty much run. No, I run like
0 miles a week. That's pretty good.
Yeah.
Every day?
I usually take 1 or 2 days a week off.
So you do 40 miles in 5 days?
Or 6.
Are you training for anything?
I said less than 40, more than 30. So now 40.
With teaching from home, I figured out I can run before class.
Yeah, I can do
awesome.
that. I can do that too.
But not 40 miles. Everything's working. We can move on.
Let's move on.
Shoot and smile. Yes, Jay is a track star.
Oh my goodness. Okay. So let's go back to our outline here. Okay. Let's make our initial wave function. Okay. Cool. Also, yeah.
This will be our wave packet.
What were the numbers that I came up with? K naught. Oh yeah, we need a mass for our particle, don't we?
It's an electron.
Yeah.
What's the mass of an electron in atomic units? Nobody in chat knows. Oh, you spoiled it.
I did spoil it.
1.
It's 1. So let's make self dot. So the initial wave function will be a Gaussian wave packet centered at x naught with average momentum h bar k naught. H bar is 1, so really just average momentum k naught. That's exciting. With
easy peasy.
Sigma. Okay, so we'll do self dot x naught is equal. I guess we can make this a parameter, right? We could pick this if we're calling these things.
So the chat figured out that I'm secretly planning a quiz based on questions in this tutorial. Jay, what are you teaching this semester?
I'm teaching quantum, Phys Chem 2.
What book do you use?
And I'm teaching a computational materials chemistry course.
What book
which
do you
is
use?
Basically quantum.
It's the same book, or same course. What book do you use for quantum?
I use, for undergraduate quantum, I use Engel and Reed. And for the graduate computational class, I use Chris Kramer's book.
Oh, okay. We use Atkins, and I'm really mad at... I don't even remember what publisher it is. I'm really mad at them. They won't give me a desk copy.
Oh, really?
Well, they've ignored my request for a desk copy, which irritates me. I feel like... Why should we ask... Whatever, it doesn't matter. I'm angry with it.
So I'm still just allowing that later on we'll specify these values, but otherwise I'm giving them the value, the sort of default values that I think are good from up here. Yeah, sigma, that's the weird one.
That's the width of your wave packet?
Yeah.
Or it's related to the width? What do you do in your computational course?
We do a little bit of everything. So we do some electronic structure theory. Right now tomorrow I will do the third lecture on Hartree-Fock. Because Hartree-Fock takes a while, right?
So they should have had PChem already?
Yes, that's right.
And this is for undergraduates or graduate students?
Graduate students.
For anyone watching who doesn't know, Jay just said Hartree-Fock. You might be familiar with molecular orbital theory, and Hartree-Fock is where the orbitals come from. It's the math form of that concept.
Okay, and now we got all of our parameters. We just got to put this ugly expression into code.
It's not ugly. It's beautiful.
Well, it is beautiful, but it's a lot of things for the old dude to keep in his memory. So good. Luckily, I have this cheat sheet over here. I've got a second.
That's what I was gonna say. You're clearly looking at another computer. Why didn't you just have the thing you need?
So let's do self.psi. So we'll call our real space wave function self.psi.
Good name.
And that's going to be equal to 1 over self.sigma times np.square root 2 times np.pi. This is one thing that is really annoying about Google Colab is like you do get a lot of help, which is great, but then these little dialog boxes pop up.
Yeah, that's annoying.
Okay.
Do you ever use Overleaf for writing papers?
I do. I love Overleaf for writing papers.
Yeah, I was going to say it's the same thing, but I really like their autocomplete feature.
Mm-hmm. Come on, get out of here. I can't even see what I'm doing.
How many students do you have in your group these days?
I have like, I think, oh, you know what? I can answer that. I have 7.
I hope you can answer that. How many?
7. No,
Wow.
7 is a hard number for me to remember exactly, but we just did a Zoom grid and we filled out all but 2 slots, which I had to fill in with June and a blank slot. A 3x3, we filled out a 3x3 grid.
That's an interesting way of remembering who's in your group. I would just go through the names of my group members personally.
Yeah, that's. I guess that's great too.
Cena's pointed out you're doing all of this in the constructor. Is that true?
Yes, I am.
At what point do you decide, okay, I should probably have an initialize function instead of a constructor?
That's a great question. I don't know the difference, honestly. What's the difference, Tina?
I have no idea. Oh, and that's why self is everywhere. But Jay was claiming that self will be everywhere regardless. Whatever. Your keyboard would last a lot longer if you got all this out of the init function.
Okay. So, all right, this is that normalization piece, 1 over sigma times square root of 2 pi. This is the spatial Gaussian part, exponential of negative 1/2 x minus x naught over sigma, that whole thing squared. And then this is the plane wave thing.
What's 1j mean?
1j is square root of negative 1. Okay.
So
There we go.
all these quantities are natively complex valued. You don't have to do anything special for complex.
Oh, that's a great question. I think this will, no, you do typically. If I declare an array, if I form a NumPy array, and I want it to be complex, I have to specify that it's complex. But I think what's going to happen, because I have a computation that involves an imaginary number, so then the results will be complex. I think it's going to
Even though
ask.
on the first line of those three it's real valued.
Yeah, I think so.
Okay.
Let's find out.
Python is magic.
Let's find out. So I'm going to run this. And now I haven't defined. Has no attribute K, duh.
K0.
Actually not defined.
Wait, the chat has caught a bug. Do you need... J. Callahan Stem says you might need self.x instead of x on that last line.
Perfect. Thank you. Oh, you're right. Okay. Let's see. Let's do this. Self.psi equals np.ones. Len self.x dtype equals complex. So now I'm going to create an array of ones with the same length as my x grid, but there will be complex numbers. And then I'm going to multiply.
Could you get around doing that by doing the plane wave first?
Maybe. Okay. Maybe I could.
J. Callahan Stem, I think you might have
probably could.
I think you might have been here last week. So thanks for coming back. If you weren't, sorry, mistaken identity.
Okay, let's do a plot of our plane wave. There's our plane wave.
Oh, it's beautiful.
Yeah.
So it's got a frequency that's related to your momentum, but it's localized to some region of space.
And let's plot the probability density too.
Woo! Do it.
So I'm going to take the complex conjugate of psi with this np.conj times psi.
Oh,
that looks
gorgeous.
like a Gaussian curve,
it sure
doesn't
does.
It? Yeah. Okay. All right, we're done, folks.
That is the demo.
That's the demo. Okay, so that looks good.
This is amazing. We're 1 hour in, and that's what we've accomplished.
That is what. We're gonna roll from here. Let's go ahead and define also.
Oh, Ali Boo Woo 2 says, "Hey Jay." That might be Bridget.
Hi. Oh, hi Bridget. Okay, so this is also going to be important. So let's define the momentum space psi as the Fourier transform of psi, and hopefully we can plot.
Sina wants to know how the radial distribution function looks.
The radial distribution. What is he talking about?
I don't know what that means either. It's just a wave packet. So, and it's
There's only one dimension.
And it's in
There's
X.
only one dimension.
It's not. Yeah. But we may be misunderstanding your question.
Yeah.
This is another thing that makes me jealous of people that use Python. Your fast Fourier transform is a built-in thing.
Yeah. So this is the momentum space wave function.
So I think the radial distribution function is r squared psi squared, but that's in spherical coordinates. So
yeah.
Here it would just be like multiplying x squared by that function, so it'd be Gaussian that goes to the moon? I don't know.
It's an interesting question. I guess I don't know. I really don't know. Well, at this point, we have our momentum space wave function and our real space wave function for our initial condition.
I'm sorry, I wasn't paying attention. That's the wave packet in momentum space.
Yes, this is the probability density
So you can see how
in momentum space.
localizing the particles made the momentum spread out. So if you had a tighter Gaussian, that one would spread out more.
That's right. Yeah, and we can do that, right? So we can do sigma equals sigma. What is sigma currently? It's
X, so whatever over 30 was what you had up above.
Yeah, 500 over 30. Let's do, so 500 over 30, we can call it, that's approximately 20. All right, let's make it smaller. Let's make it 5.
So that should, so if it's smaller, that spreads out this, no, that tightens the spatial.
Tightens the spatial component, which spreads out.
If it's smaller, shouldn't it have?
Let's plot the real space.
I thought if it's smaller, it should spread out the wave function.
Yeah, the real space is more tight.
Okay.
So the momentum is more spread. This is progress, I think.
My calculator on my phone agrees with you.
Okay, good deal. Okay, so now let us do a couple of more things. Yeah, this is all still in the constructor, but I'm gonna write at least 2 methods coming up in just a bit.
You're gonna have a constructor that's 15 pages long and then 2 methods. Perfect.
Yes. Okay. So let's define v hat, right? And so right now,
Let's just make it 0 for now. So we'll just have our
exactly.
Yeah. What does the like mean?
Oh, it means of the same shape and data type.
Okay.
So this is a good way to get a complex. If I did it like psi, it would be complex.
Can we do a complex potential later and watch the wave function die? Something like that?
We can, yeah. Well, I think we can do that. That is, you can pretty much do the split operator with a complex potential, but you just have to adjust the norm of the wave function each time.
But I want to use it like a complex absorbing potential.
Okay.
But never mind. Let's do the actual thing that's going to take 3 hours, and then we can do more things.
Yeah. So k hat is going to be, what did we say? Self dot p squared over 2 times self dot m, right? I think that's what we said.
I think there's a pi in the denominator. No, I don't remember. I think
that's it. I think that's
you're right. It's p squared over 2m. It's the
yeah.
Yeah.
Okay, and at this point, yeah, let's one other parameter. We need a delta t. And I actually don't remember. Yeah, let's put that back up here. If time step in args self.dt equals args time step.
Why do I use C and C++? This is so much better.
I'm just going to do 0.1 for now. That's atomic units. That's a really short time step. Maybe I'll do 0.5. Right, everything we're doing is in atomic units, by the way. I don't think I said that.
H bar is 1.
H bar is 1. Okay. So let's do the following. Let's build our operators. Except for, yeah, let's build our, let's do, let's make two methods. Oh, sorry.
Should that not be indented?
I should be indented after this. I think the def goes in line with everything else, I believe.
Okay. I don't know anything about Python classes, so I believe you. Anyone learning Python, one of the annoying things about Python is like white space is meaningful. I think it needs to be back. Chat says it needs to be in line with init. Is it?
Oh, thank you.
Because it's a different function. So yeah, when you end that indent.
Yes. Thank you. You're right.
Tabs or spaces, Jay?
I actually like spaces.
It's the right answer.
Is that the Richard Hendricks answer?
No, he tries to run down the stairs and he falls. He tries to go down 4 steps at a time.
Oh my goodness. This whole thing times k hat.
That was a Silicon Valley joke.
Yes. I love that show.
It's a good show. You have got to be kidding me. That's the entire function?
Yeah, this is amazing, right? Like you can just exponentiate,
No, I mean your constructor is 400 lines long and you decided, I'm sorry, this function is far too long to include in my constructor.
I really am getting so tired of that. Why do we have to be?
What are you doing this? What are you writing in? What's Colab? I don't know what that is.
Oh, this is like Google's, is this like a Google environment for Jupyter notebooks?
Do they own your code now?
Probably.
Sorry, big money research VC.
Okay. All right. Hey, we're getting really close though. This is basically this is basically one of the last steps before the split operator. Yeah. Okay. I need a pause. I'm going to sip some water and maybe some of my wine.
Cheers, Jay. Thanks for joining me.
So I guess at this point, since I have, so let me just clarify. V hat and K hat are the real space and momentum space, potential and kinetic energy operators, respectively. And then K and V are the exponentials of those operators.
Okay.
So maybe a comment.
I was kind of wondering why you were using, I thought, oh, what good programming practice. He's being extremely explicit, calling it K hat. I didn't realize there was a K coming.
Yeah. I should say this builds.
So you're 7 students whose names you don't know, but you know how many squares there are. Are they?
No, I know their names.
Oh, okay.
There is.
They're It's not a test,
You want
Jay.
me to name them? Or are you testing me? There's
No.
my most senior students are James, Penny, and Fegan.
Shoot and Smile is here. They claim to be one of your students.
Who is it?
Shoot and Smile.
Shoot and Smile. I don't know that name. My first year master's students are Jose and John, and then I have an in between named Ben, who's not a first year nor a second year.
So,
And then I have an undergrad named Alyssa.
what was the first group?
Penny, Fegan, and James.
No, I mean, are they graduate students?
Yes, they are, right. And Fegan actually finished this fall, and Penny and James will finish this spring. Did that funny screen name identify themselves?
Nope.
By actual name? Okay. So let us also, let's just go right into the split operator, right? Okay.
Shoot and Smile streams games. That's where the name comes from. When they shoot you, they'll be smiling.
Okay. It could be John or it could be Jose, I guess. I know they both like games.
Lactase TV, I don't know. Maybe you should blame Jay if you're lost. He's the instructor here.
What's going on?
Scroll back up to the beginning and tell everybody what you're doing.
Okay.
He's got a wave packet that he wants to propagate in space.
We have a wave packet that we want to propagate in space.
Why don't you just show us how far we've gotten? Yeah.
We're at step 6, believe it or not. We just formed the exponentials of v hat and k hat. So now we just have to implement this.
Awesome. Everybody's just here for the pretty pictures.
Yeah.
So let's do it.
Okay. Okay. So first thing we need to do is our partial update to psi from v.
I don't want to get you too excited, Jay, but Big Money Research VC thinks you're doing a great job.
Oh, thank you.
Money forthcoming.
Okay.
That is really annoying.
Okay. It is really annoying. Okay.
Can you scroll up a little bit?
Yeah, thank you. So first we're going to do this partial update from v upon psi. So we're literally just multiplying psi by the exponential of v. And this is the unity operator at this point because we have no potential, but that will change. Then we're going to Fourier transform psi in anticipation for hitting it with the k operator. Actually, I should clarify, this is a full, so that's something kind of funny about the split operator method. You have those, that string, which is this approximation to the product that ignores the non-commutating terms. The bread on that sandwich are half steps, and the meat is a full step. So in this case, we chose the bread to be the potential. So we do a half step with potential, full step with momentum, half step with potential. But you could do it the other way too. There's nothing that prevents you from making the momentum the bread and the potential the meat. Or it doesn't have to be meat. You know what I mean? Meat substitute, whatever you like. Okay. So we got the inverse Fourier transform. So this is the applying k to the Fourier transform of psi. So then we have to inverse Fourier transform. Oops. Self dot psi. Yeah, I do remember doing fast Fourier transforms in C, and it's very annoying.
Yeah.
I mean, it's okay, right? It's only like 3-ish lines of code plus.
Well, you have to find the library. You have to link to the library. You have to find the call structure. You have to realize that you are putting in discretized data and you're getting out discretized data. But here you don't. All that's hidden. So you just say psi is this Fourier transform. It's much easier. I'm so jealous.
And I think for good measure, what we should
CNIP.
do is after
I
we
agree with
finally
CNIP.
updated our wave function in real space with this last step, we should also take a final Fourier transform so that we're always carrying around the most up-to-date momentum space, right? I think that.
Oh yeah, to do after your half step, yes.
Yeah.
Or yes.
Uh-oh. Did I not unindent enough?
It's your comment. Oh no, you're right.
Before I unindent
that's-
everything.
I don't think that's.
Okay.
Did it work?
I think it worked. All right.
What are you plotting? Oh, that's still just the
that's
square of the wave function.
That's right. Okay. So then, what I need to do is fill in my animate function here.
Can you scroll up a little bit? Just a couple lines.
Yeah. Like here.
No, I just wanted to be able to see the animate function because I'm in front of it.
What do you want to see?
Are you working
the
on
animate?
it? Yeah. Perfect.
Okay. So basically, I think all we need to do, besides creating the instance of our quantum class and building the operators, then we can basically go in this animate function. So this is something that, again, I have to confess, I don't really understand many of the nuts and bolts, but there is this matplotlib library called Func Animation. And basically what you do is you give that some driver function that advances like a time variable that changes something that you want to plot. So in essence, so I'm calling that animate in this case. So there's a function called animate. And basically what I need to do is set, I call the split operator method in def animate and store the output, so the wave function and the X grid, to this line object, and I also optionally the potential to this line V object. So I'm imagining that I'm going to plot both the potential and the wave function at each step. And I think that's kind of it.
Are you supposed to have the comma at the end of that function call?
I am.
Why?
And
Is it
I would love it
expecting
if
more
someone could
parameters?
explain to me why.
Is this expecting a third parameter that's optional or something like that?
No, it's not. I don't believe so. I think it's somehow it's like part of this object, I think. Explanations would be appreciated. But I don't know. I don't know. Okay, let's just give this a try. So we got this thing called WF. That's our wave function object. Let's do WF dot build K operator, WF dot build P operator, and here.
Yeah, why do line and line V have commas up there?
Yeah, I don't know. I really don't. I don't. But I believe me, I've tried to delete them. um, and then everything breaks.
I'm so excited.
Okay. Well, let's just see what happens here. Everybody ready?
I'm ready.
Ax is not defined.
What's ax?
That's this right here. AX. Okay, I gotta cheat now. Oh, okay. There's extra stuff that I think I deleted.
More commas.
That's right. There's not nearly enough commas here. Okay, now it's working. Something's happening.
Oh, I'm so excited.
And we still have 15 minutes to troubleshoot.
Oh, we've got longer than that. 90 was a minimum, my man.
Oh, that's right. Okay.
Unless you have to leave. Oh, it's 0.
That's fantastic.
That's great. That's a really good line.
Oh,
Do you
goodness.
deliver your courses in person or remotely?
All my lectures are. I actually Phys-Chem is remote lecture and then in-person lab, and then the graduate course is the opposite of that. We have a computational lab, which is remote, and a lecture, which is in person. Okay, let's see what's going on here.
Do you teach the lab too?
I do. I do.
Rainley 323 is asking if line V needs set data in animate.
Yes. Oh, yeah. Oh my gosh, that's what's going on. Thank you.
Nice,
Yeah, I think what was
nicely
happening is
done.
I was overriding the wave function line with the potential line, which is zeros. I think you saved me. I was going to stare at that for 10 more minutes.
It's thinking. That's
It
something.
is.
So how do you do your? Oh, all right. You need
That's
bigger.
good.
You need bigger axes.
This is very strange looking. Yeah. Let's do it like this. I think this would be a good. These would be good axes for the
Square modulus.
yes.
It takes so long to initialize because your initialize function is really long. Lactase TV is taken off. See
There we go.
See me Friday. I'll see you Friday, Lactase TV. Thanks for stopping by.
All right, so here we have a real wave packet spreading, and evidently we have periodic boundary conditions. That's cool.
Is that a mistake, or did you just forget that you coded periodic boundary conditions?
So that's no, I didn't. I mean, I think it's either a mistake or somehow that's natural. I mean, I guess it's no. So I guess it is. I have to think about this, but I wonder if it's somehow in. Yeah, I wonder if it's somehow in the p squared over 2m operator.
I think big money research VC, in order to invest in us, wants to know what the heck he's looking at.
Oh, okay. Well, you're looking at the probability of finding an electron as it's traveling. So this is something that is actually in itself. I know this is a boring movie, but
I think it's beautiful.
You think it's beautiful? Good. Already tells us something. So normally when you think about, like, if you thought about tossing a tennis ball across the room, right? The probability of finding the tennis ball would change as it traveled, but it's not as if it would become more spread out in space, right? It's not like the tennis ball starts to kind of like
dilate.
It doesn't dilate as it travels, but an electron does. So this electron is starting out this much localized, right? But then as it travels, it spreads and becomes more and more delocalized. Okay. So its position becomes more and more uncertain as it travels. And what is hopefully going to become interesting is if we actually put in a potential here. So let's do that. We can do that.
I don't believe that your periodic wave packet is correct.
Have you really thought about
space?
The momentum space operate? You may be right, but I'm kind of thinking that the way that our momentum grid is set up. No, I don't know. I really don't know, Eugene.
I guess I could believe you. I'll just believe you.
It definitely doesn't have a hard boundary.
That's correct.
Right? There's no hard potential. So let's put in a potential. Let's do a couple things. Let's also.
So you changed sigma to 10. What did that do?
That should make it.
Quantum mechanics does take trust.
Yes.
You have to trust the process, first of all, and take it from there.
So let's put in do you want to put in a square well potential or square barrier?
That sounds amazing.
Okay. So after we create our instance WF, let's do WF v hat, and I'm just going to kind of, every one atomic unit in X is one index. So let's do v hat 400 to 499 equals 0.1. And run that.
So again. It's just going to hit something at the very edge.
Yeah.
Okay. This is exciting.
Let's hope we actually get the barrier. There's a big barrier. Okay. Let's go. Oh, second hit, it's running out of steam. It's too afraid. Okay, let's move it to the right a little bit.
Can you make the K bigger?
Yeah, we can make the K bigger. What was that parameter?
K0, I think. That will, I know that you know this, so I'm saying this to everyone watching. If you make K bigger, that will make the momentum of the particle higher so that wave packet will move faster.
So right now it's 1/2. Let's make it
0.8.
Let's make it 1.
1? Wow. I like this. There's a drink break every time you hit enter.
There is.
Just like real quantum chemistry research.
So what are you teaching right now, Eugene?
I'm teaching the second half of the PChem sequence, which is the quantum half.
Okay. And what did you cover this week?
Harmonic oscillator. We actually did tunneling. Oh, it went right through that barrier. We actually did.
It sure did. Oh my gosh, that's insane.
You did give it twice as much energy. I don't know.
This doesn't seem right at all. I'm very suspicious of this, Eugene. I have to say.
Try ticking back down your
my K.
Your K.
Yeah, maybe that's
but
it.
I mean,
but
like,
I have a feeling something else is wrong.
Awry.
Yeah.
So yeah, we did harmonic oscillator this week, and we did tunneling last week.
Okay.
But we don't do it. We just do the standard tunneling problem, not in terms of a wave packet.
Okay. I also did the harmonic oscillator this week.
Fun.
Mm-hmm.
That, you know what? Entangled AF. That's a fun name. Oh, that was Big Money Research TV. They said that doesn't look like exponential decay. Entangled AF. Late, but I will watch the earlier stuff later. What about 2 electrons? Could you... Oh, hey, it worked.
Yeah, this is... Okay, so maybe the momentum was just really, really high, and then the tunneling... Yeah, so this is a really good... point that entangled AF is making. So
it doesn't matter. Yes.
So this is one really important distinction here. We're not looking. So when you and I also, I don't know if anybody was looking at this on Twitter, but our friend Justin Karam said something on Twitter like WKB or get the fuck out. So I just want to connect. If people know what WKB is. This is a way of finding the stationary solutions for a wave function with a barrier with tunneling. And so if you have done a problem like that, you've gotten these stationary states. When you look at the harmonic oscillator, you're also looking at stationary states. So those are wave functions that have a precise value of energy. This is not a wave function with a precise value of energy. This is a wave packet. It's got many different energy contributions. So your stationary states, they do have to have a particular property in the tunneling region. They have to have this exponential decay. Like that's part of how the way that those stationary states have to behave in the tunneling region. I'm not really sure if it's I mean, fundamentally, the wave packet that enters the tunneling region, right, it has to be built out of stationary states. I mean, you have to be able to build it out of stationary states, each of which is going to look like an exponentially decaying function. But I think it's going to be very complicated to sort
No,
of.
but hey, thanks, Oliver. I think that this thing clearly isn't decaying very much. So are those not components that have energy high enough to get over the barrier? So if you just made your V bigger, it might look more like we're expecting it to look like.
Yeah, so let's make the V bigger. Sure.
All of the Oliver, you missed all of it. Entangled AF, thanks for the follow. So entangled AF, you asked about what about 2 electrons. So you could do that with 2 wave packets, but then you'd also have to have electron-electron interactions.
And anti-symmetry.
And anti-symmetry. Wow, I didn't even think of that.
Yeah.
So that greatly complicates things.
It does greatly complicate things. So we have a static potential now, right? The potential doesn't depend on the coordinates of the wave packet. Oh, there we go.
Boom!
So we made the
That's a good reflection. So it's too big now. No tunneling.
Yes.
That's
cool. So we want to find a sweet spot. Let's find the sweet spot. Oh, that's sigma.
Oh, no.
I'm just guessing value.
Gotta start somewhere.
Should we make a well next?
Yeah. Or two square well potentials, and you can trap the particle in between them.
Oh, yeah. Okay.
Why does the reflection change the packet's values like that? So you see that when it reflects, it spikes. Why is it spiking?
Oh, yeah. So it's spiking because of interference. So we're looking at the probability density. Maybe we can look at just the wave function as well, in which case I guess we're going to have to. Yeah, this is a really good question because right, so like the wave function itself is this complex quantity. So now we're going to look at the real part as it's traveling, but there's also an imaginary part. And so both the real and the imaginary part can have positive or negative values. And so there's this possibility for constructive interference or destructive interference, both the real and the imaginary part of the wave function. And so in the end, all of that interference stuff, right, you figure out what it does to the wave function, then you have to take its, what do you keep calling it, Eugene? The modulus?
Square modulus?
Square modulus. Take the square modulus.
Is that not what it's called?
Yes, it is. I just couldn't remember. Oh, this is weird. So you look at the little wiggles in here.
Why is it starting right at the boundary? Right at the barrier?
Yeah, I don't know. I think the spread is significant enough. Let's back it up. And let's make the
Is this on your laptop?
Yes. But actually, I think I think this calculation runs like in the cloud.
Oh, really?
I think so.
Oh, that's a cool looking wave packet. Ugh, you need more time.
I do. Cool. All right. What kind of potential do you all want to see?
What are the choices?
I guess anything that we can write a function for, right? Anything that we can evaluate as a function along x.
Sina wants a spherical potential, but we're working in 1D. I think he's messing with you. Entangled AF wants a V-shaped potential.
Okay, we can do that. Yeah, sure. So, let's see.
So you want it to be 0 in the middle of the box? Is that what you want? Or 0 somewhere
I'm
else?
thinking that he or she wants a like do like that, like a V. Let's say
Yeah, that's what I meant, but I feel that's what I meant. Like,
let's see if we can figure this out. So
Entangled AF really wants 2 electrons, but J can't do that because he is not good at anti-symmetrizing wave functions on the fly.
yeah, that is going to be very
And Oliver wants to 1-up Entangled AF. They want 4 electrons.
Okay. So let's just try.
What are you trying to do?
I am trying to do a V-shaped potential.
Why are you making it lower in energy than everywhere else?
I'm trying to put, because a V is concave up.
Yeah, but you're going to start with more energy than that, so your particle's just going to go right over it. There might be a little bit of scattering, but nothing much will happen if the potential's negative.
You want to do it the other way?
I think that you should do it like all the way from 0 to 250 to 500. 0 to 250 have a negative slope, and 250 to 500 do a positive slope.
Oh, okay.
And so your wave packet will kind of be trapped in the middle of the box.
Okay.
So it would be like harmonic oscillator, but not harmonic.
Oh, yeah. So
your students are difficult, Jay. All of the Oliver wants M shape.
Isn't that like the absolute value function?
Yeah, that's perfect. But you probably need to scale it.
Yeah. Oh, yeah.
What's the problem? Could not broadcast.
Oh, yeah. Sorry. I still have this like slice of V hat. Okay.
Boom.
Yeah, there we go.
That's beautiful.
What do we want to scale it?
Thank you, Jay Callahan STEM. Chat got to it before you. Did you know that's what the potential looks like for a vanadium atom?
No, I didn't. Is that a joke? V potential is for vanadium. Okay, this is gonna
Why do you think it's called vanadium?
because of its V potential, of course. Okay, yeah, let's give this a shot. This is gonna be cool. This would be a good opportunity to look at the momentum space dynamics as well.
I concur. Entangled AF wants an approximate potential for Dirac strings. There's a statue of Dirac outside my office, and I don't even know what that means.
Can you chat us the function?
Oh, that's what this potential is. Really? Whee!
Really struggling. At the end, look at it. Oh, it's so close.
Make it steeper. So it's just like...
Is totally trapped.
Yeah.
Yeah. This is I think it's really misleading to look at the probability density. Make it 5 times steeper. I mean, 10 times steeper. Yeah, okay. Let's go for it.
I can't believe you have 7 students. I only have 4 students and a postdoc.
Well,
anyone listening, I need many more students.
You should try being nicer.
I'm very nice. Oliver, why don't you come do a PhD at FSU and you can be in my group? It's still left.
It's still left.
Give it less kinetic energy, maybe, and make it steeper. I don't know.
Yeah, we're
too many parameters.
Smaller sigma is, the more uncertain. Yeah.
I'm not talking about uncertain. I mean K. Make K smaller.
Yeah, I guess I could make K smaller. I'm not going to do that, though.
Well, we'll see if this works. Florida is very cool. Well, it's actually warm. It's supposed to be 80 at the end of this week.
That's amazing. Wow. It felt like 60 today.
And you were in heaven.
Do you know how much snow we've had, Eugene?
No, probably a lot.
We've had a lot. We've had 50 inches.
No way.
Since January, yeah. And today it felt like 50, which was awesome. It's starting to feel like, you know, that scene with William H. Macy and his car and the what is going on here? I'm so perplexed by this. It's like it doesn't even care about the potential. I don't know. I don't know what's going on. I don't know what's going on here.
Make V bigger. I told you to make K smaller. You didn't listen to me.
Yeah. I'm starting to wonder. Is my grid even big enough?
Doesn't change the fact that the particle just wandered off.
Yeah. You know, if we were smart, what we would do
is make K0 smaller.
Yeah. We would figure out, you know, like what's the highest momentum component in this thing.
Yeah, you could plot the momentum space wave function.
Yeah.
Well, I mean, it's going to spread out in momentum space, though, isn't it? Isn't it going to?
No,
It doesn't spread out. It only spreads out in position space.
I think so. Let's confirm. What the? Oh God! I just like.
Did you make K0 smaller yet?
No, I didn't make.
You are the worst.
I know.
What's the most exciting project you're working on right now? Aside from this, of course.
I am. I have to say, I am really excited about the ab initio polaritonic structure methods because it's been so long since I. Oh, what is going on? Oh man. Okay.
Oh,
You know what
it's
happened?
bouncing around at least.
It is bouncing around. I think we finally did it. But since I like didn't play the animation, I ran that animation twice. So it's just picking up like where it left off at the end of the last animation. Okay, yeah, this looks an awful lot like the dynamics and a harmonic well. So I think we're finally doing something right. Okay. Yeah, I am really excited about that because it's been literally, when was 2012? It's almost 10 years since I've really done any electronic structure method development. So it's good to be back.
Good to have you.
And I feel like things are so much better now with, I mean, Sci4 compared to, hacking things into games.
Oh man. So
It's like,
when Jay and I were in graduate school, it was like a major breakthrough for us when we figured out how to print a whole bunch of integrals in binary instead of in ASCII text because it took up like 10 times less space on disk.
yeah,
Nobody cares what we're talking about, but man, it was so ridiculous.
yeah, this whole thing with like the mints helper and stuff. Oh, it's amazing. It's just like, it makes me so happy.
Does anyone in the chat even know what Sci4 is? Brainley323, are you still here?
Oh, speaking of which, Eugene,
Yes.
is it like if I want, because you said something when we were chatting, like, oh, you should do TDDFT polaritonic structure as well. And I figured you meant like linear response, so like the equations are like basically TDHF, but I need the exchange correlation integrals.
Yeah.
Are those easy to get? Like, I mean, if I run, a DFT calculation in Sci4,
So I think
can I use Min's helper to get those exchange correlation integrals?
I think that either TDDFT is implemented or it's in the current version or it's soon to be released.
You are correct.
So it's there. I just don't know how you grab it. The problem with the polaritonic stuff is you also need the electron-photon correlation functional. So you have to do whatever Rubio does, solve some OEP equations.
Yeah.
So what Jay's talking about, Jay and I are both quantum chemists, so we usually think about electronic structure, solving the Schrodinger equation for electrons. But we're both also interested in photon-electron interactions. And then you have a second type of particle, and there's correlated motion between electrons and photons, just like there is between electrons. Save failed.
It's really strange. It's like someone has my notebook.
Did I share it with anyone?
I don't know. Is someone else changing my notebook?
Rain is still here. No way. Jay Callahan Stem said he did
it. Okay.
We can't see your animation. Were you trying to show us?
It's okay. All right. So this is cool. We've trapped it in this.
It's available on your GitHub.
Yeah, but like, I made a new copy of this. I
Oh.
thought. I thought I made a clean copy. Oh, well. It's okay.
We have to start over.
Let's look at the momentum space wave function. This is
Jay, I'll be right back.
okay.
So you have to keep talking. That's the key.
Oh, that is the key. Okay.
I'll know.
I know. All right. So I'm going to look at the momentum space wave function trapped in this potential. We won't be able to see the potential, though, because our momentum space wave function does live on a different grid. The real downside of Eugene leaving is I'm not connected to the chat. So if anybody's chatting anything, it's going to be like impossible for me to know what you're saying. So I guess I'm just going to talk as if no one is there. Oh, that's really bad. Let's see. I gotta go back to this thing. So my momentum grid goes between -6 and 6 approximately, not 0 and 500. What's the magnitude? 1.5 and 5. I should have commented all this stuff out because I'm probably going to need that stuff later if we want to look at the real space again. Thank you. That seems like the sound of someone pouring some water. Okay, I think this should get everything set up properly. Let's see if this looks better. And we're going to plot the real part of the momentum wave function. We should really look at the distribution. I mean, the probability density. The square modulus. Okay. Everybody's gone, Eugene.
Everybody left?
They all left when you left.
No, they didn't. There's 20 people here still.
Oh, I see 0 viewers.
Really?
I don't know. Don't believe me. So this is the momentum space wave packet. That's pretty cool.
But what does it mean, Jay?
It means, I guess, the momentum. So first of all, I guess the momentum is spreading. I wonder if the momentum only spreads when there's no potential. I mean, only doesn't spread when there's no potential. Okay.
I don't understand how the position can spread, but the momentum doesn't.
Yeah, I know, right? That's kind of funky, isn't it? Well, here's one thing. With no potential, momentum eigenfunctions are also energy eigenfunctions. So they're stationary states, right?
Yes. Entangled AF says free particle keeps the same momentum, but you have no idea where the probability density for a free particle is uniform. So it's not spreading out, it's infinitely spread out. I feel like you can't have a particle spreading out and have exactly the same momentum. Maybe you can. This just doesn't make sense to me.
No, you can. Okay, so you can. Oh my gosh, this is so freaking weird. Do this again. Do this again. So, okay, the free particle, right? This is no potential.
Plane wave is totally
And
spread out. That's the free particle. Yeah.
right. And then, so you've got your energy eigenstates are also momentum eigenstates. And you have no problem believing that the energy expectation value doesn't change for a wave packet
Okay.
in free space.
You've convinced me.
Okay, good. There we go. Here's our momentum space wave packet in that well. So that is cool. That's very weird looking.
But okay, hear me out. Thought experiment. If I had a momentum space packet centered around x equals 0,
Yeah.
it would have an expectation value of 0. Expectation value of momentum would be 0. Yes.
Yeah.
And it
Sure.
spreads out. What's the expectation value of momentum? Still 0.
Yeah. Okay. Fair enough, but also the expectation. Oh, right. So I asked you about the expectation value of energy. I should have also asked you about the uncertainty in energy. Doesn't change, right? It's still exactly the same superposition. Your wave packet, right? You can expand it in the energy eigenstates, and the coefficients do not change in time, right? If there's no external potential that's changing in time.
Which coefficients are we talking about?
So do I have this in?
We're picking up viewers as we argue about this.
We are, okay. So let's take this wave packet, right? Now I'm going to start typing some things. Where's my?
I'm going to pull up my iPad. Let's go.
Let's go. Okay.
I don't know where it is though.
So let's say that I want to write my wave packet as
If you scroll up,
superposition.
it's right behind me. Those C's don't change.
Those C's don't change.
But the overall coefficient in terms of any given momentum function changes because that's not a stationary state anymore. Because you have a sum of stationary states.
That's right. You have a sum of stationary states, but because the coefficients don't change, right? Your energy expectation value is just what? It's some like this. So the energy expectation value doesn't change.
That's not true. It's not a stationary state.
No, it's not a stationary state, but the energy expectation value is just the sum of these square modulus of the coefficients times the energy eigenvalue, right? So if I had, a superposition that was an equal admixture of psi1 and psi2, right? So then what's the energy expectation value at T0? It's just 1/2 E1 plus 1/2 E2. What's the energy expectation value sometime later? Same thing. And then the only other question, right? What is the, what's the energy expectation value of E squared? Because you need that to get the energy uncertainty. It's the same it still actually works out to be this expression.
I believe you.
So as long as your energy eigenfunctions are also your momentum eigenfunctions, you would make exactly the same argument. And that's true as long as there's no potential. As soon as there's a potential, then your energy eigenfunctions are not your momentum.
Why are we arguing about this? Where did this come from?
Does
the momentum spread out?
Momentum spread. Does the momentum space wave packet spread? And the answer is no for the free particle, and the answer is yes if there's a potential. This is great. This is like a really heart of quantum mechanics discussion.
It truly is.
Okay, it's 10 o'clock. I think.
Are you done? I put on the schedule that this was 3 hours, Jay.
I think I'm getting ready to wind down.
How lame.
I would entertain another potential if someone has one.
You would? The chat wants to know, how is the momentum grid defined again in the code?
Oh yeah, absolutely. Do you want to see the code or the expression? I'll show you both. The momentum grid is kind of defined in a funny way. It's got 0 to n grid points divided by 2, and negative n grid points divided by 2 to 0, all multiplied by this grid spacing and momentum, where that grid spacing and momentum is 2 pi times h bar divided by the number of grid points times the spatial grid spacing. So that's the code, and then the mathematical expression is here.
Rainly323 says 1 over R potential, a string of delta potentials. What?
Say that again.
A string of delta potentials, 1 over R potential. A string of...
Oh.
Like at every point?
We could do like the Coulomb potentials and the delta potential. Let's definitely try to do... yeah, let's definitely try to do the Coulomb potential. That would be fun, I think.
Except your particle's going to have too much energy. Just, I don't know how you make sure it doesn't skip above all the potentials.
That's true.
Well, that would be negative 1 over R.
Or I guess it could be a Coulomb repulsion. Oh. Same bug every time. That's not what I want exactly.
We have been provided tuple syntax. What are you trying to do?
I'm trying to make this 1 over r potential that they were talking about. I don't like that. Let's go with something like the delta function. Although the delta function, there is a delta in...
Entangled AF suggests abs.
Oh, yes, thank you. Thank you. There we go. Thank you. Yeah, this will work. Okay.
So wait,
Let's move it over. Okay. Let's go back to real space. Momentum space was too confusing.
is anything interesting going to happen with these delta potentials? It's
I don't know.
so thin.
But it's also
So
is so yeah, it's very high. Okay. Let's give it a try.
And you still don't want to play any video games.
No, I don't think so.
So lame. You never liked any video games growing up?
No, I did. What's going on? Here we
Woo!
go. Ooh,
Oh.
really hit that. I like it. That's pretty amazing.
So since it's... What happens... It's infinite, right? So can you... Is it just like an infinite potential barrier?
I guess it is, yeah. I mean, it's as close to infinite, I guess, as you can get. Yeah. Let's do that one more time. Yeah, I had like the old school Nintendo and Sega Genesis. So,
But Jay, do you understand, with the power of the internet, you have old school Nintendo at your fingertips?
I did not understand that. No.
I guess you can't get past it.
Yeah, I don't think you
I
can
suppose
get
that makes sense. Infinite. It's a delta function,
Yeah.
right? That's what we're looking at.
Yeah. You can't see the potential anymore because I zoomed in.
Also, it's
To the-
infinite.
Yeah. Oh, this is great.
That's cool.
Yeah. I like it. That was a good suggestion. Okay.
Any other suggestions? Can I show you the thing I made today, Jay?
Yeah, sure.
So,
Wait, stop sharing.
it doesn't matter. Sure. So today I was... See you later, Entangled AF. I was playing with this as well,
Okay.
but I was doing it in a different framework. I picked a box, and I expanded a wave function in terms of particle in a box wave functions. And I wanted to see if I could tunnel through a barrier. But I never got it working, but I can at least slam a wave packet against a wall.
Yes.
You ready? Here it comes.
Yeah.
How exciting is this? Pew!
I'm waiting for it.
It's just, well, there's a delay, you know. Pew! Bounces off the other wall. But there's something wrong. Whenever I put the potential in the middle of the box, there's something wrong with what I've coded. I don't know.
Oh yeah, I like it.
So here the blue is the probability density and the green and the red are the real and imaginary components of the wave function.
I do like this a lot. That's great.
And it says tunneling, but it's clearly not tunneling.
No.
Vaporwave, bro. I don't know what that means, but yes.
No, this is super cool. Also, if you let these things go long enough,
Oh yeah.
you know, like, it starts to reemerge as like its initial wave packet. I mean, I guess it has to. I don't know how long that takes.
There's a term for that.
Is it the recurrence time?
Yeah, recurrence time. Okay. I mean, it has to happen eventually. I guess.
What are you using to animate?
Thank you. Super exciting. OpenGL.
Oh, okay.
I don't know what people in my I don't even think big money research VC is from my class, but people in my class were saying poggers. What the world does poggers mean? I have no idea. I do if it's not going to get me arrested for knowing. Is it a normal thing? Does it just mean super excellent? I'm too old. You're not allowed to tell me. Look, I'm the butt of a joke. How great. Anyway, that was what I did today. I swear I almost had the tunneling version working, but it didn't quite work. Pog means cool. It's good connotations, okay. I am the Pog champ. Well, does anybody have any more questions for Jay? You could ask anything. You could ask about graduate school. You could ask about careers in academia. You could ask about Python. Anything.
It is actually not too late to apply to graduate school at William Patterson. If you want to get your master's in materials chemistry, you can still apply.
Cool. How long is your master's program?
2 years.
And how many courses do they have to take?
They have to take, that is the excellent question. It's something like 8, but 4 of those are research courses.
Okay. Hey, so hold on. Sina, come back next whenever this happens. It's going to happen often. I'm glad you enjoyed it.
Yeah, it was. Take care, Sina. Thank you for stopping by and for asking good questions.
I think the question from Big Money Research VC is for Jay. Did you make a snowman recently?
Yes, although it was not very good. The snow has not been very good for snowman making or snowball making or anything. It was either too dry or way, way, way too moist. Yeah.
Bummer.
But I tried.
Does it have a nice crunch?
It does now, for sure. Because now it has gone through many freeze-thaw cycles.
I would think it's thawed now. It's 50 degrees, you said.
Well, we had, a lot of snow. So not all of it's thawed.
As I'm saying this, I'm remembering Chicago and like the crap on the side of the roads that stays there until June.
Yeah.
Well,
all of the Oliver, you will never understand PChem. All of the Oliver, are you in my PChem class?
Yes.
Yes. Okay. Thanks, Oliver, for coming. Excellent. Oliver asked me for the link today, so I had a suspicion that he might come.
Nice. Are any of my students here? Probably not. Because I'm giving away free points. Hey, Dr. DePrince. Big Money Research VC. Are you my student? A scary game. I don't know what a scary game is. There aren't free points. I don't know what a scary game is, so I'm just going to play Mario until Jay goes away.
When you say you're giving away free points, do you mean like, shares of our startup?
I mean points for like my class.
You get 3 points of our startup for attending. What those points are worth will depend on how much money Big Money Research VC has. Yeah.
Check
absolutely.
out Faith. I don't like scary things though. I get scared.
Yes. I will come up with in addition, I will come up with almost free points on the midterm for attending. But the good thing is this is going to be recorded, so then everybody can get those points by watching. It's not just you.
Well, that doesn't seem fair. They should only get points if they engage in the chat.
No, I know what you're saying. It takes particular effort to show off, but there's people that work or whatever else. So
I suppose that's fair, Jay.
More fair. Okay. Hello, Eugene.
You can't leave until I beat the game.
I don't think so.
What?
I don't think so.
I'm like halfway done. Come on, man.
I don't know how this game works. That 6 a.m. text message was just preemptive.
Dude, it was like at exactly 6 a.m. It was like you were sitting on your phone waiting.
This is preemptive revenge for keeping me up way too late.
Okay. Hey everybody, wrong warp.
What time do Olivia and Adeline normally wake up?
That's the thing, they don't get up until 7.
Oh wow.
We've got it made.
That is cool.
Like Olivia doesn't get up. If we didn't have school to take her to, she wouldn't get up until I messed up. She wouldn't get up until like 7:45.
Oh wow. That's very nice.
Adeline, we have she's got a sound machine. I assume June does too.
Yeah.
And it turns green in the morning. That's when she's allowed to get up, and she adheres to that pretty well. It's kind of amazing.
That is. So you're playing this on your computer?
Yeah, you see the name of the program, FCEUX. You can just download any game you want. It's kind of crazy.
Oh.
I only learned about this, I don't know, 6 months ago.
Is this what Ken does as well, or does he actually have a...
Oh, he's got like he has, I don't know, 200 games or something. Not only do professors play, but I have a top 500 time for Mario speedrun. My best time is 5:13. And this other guy, Ken, we're talking about, he's got like a top 200 time, something like that. This is definitely not a championship speedrun.
I'm going to close my wave packet simulation now.
Okay.
I'm not sharing my screen.
Not Pog? It is Pog. Not Pog. All right, Jay, I only have one life left, so you can leave whenever I die.
Okay. Well, this was a lot of fun. Thank you for having me on.
You are welcome back anytime, because this was way easier with 2 people.
Yes, you can. If only Mario were fully quantum, then he could tunnel through some of these barriers. All right.
Tried.
Well, yeah, we'll have to do this again.
No, Jay, don't go away. Seriously,
Okay.
this is like pathetic how I'm doing this, but look, I'm at the last level. Giant bags of mail are in the money. Sweet. I mean in the mail. Sweet. Oh my god.
Thank you, Big Money Researcher, VC.
Almost done. I'm cheating so that I can actually finish. Oh my god. Hey look, Jay, I beat it. Do you even care? Are you looking at the stream or are you just playing on your phone?
I am. No, I'm looking at the screen. I realize that it's not like my phone is. I have Switch open on my phone.
Well, this was the greatest day of my life because I beat Mario on the internet.
Awesome.
Thanks for coming, Jay. This was great. I really appreciate it.
Sure. Hopefully.
Everybody who's still here, I'm going to try to do this once every week or so. I won't always have a guest. Probably the next one I do, I'm going to do stuff that's related to couple cluster theory, which is one part of my research program.
Oh, that would be awesome.
Yeah, I'm actually going to do a normal order tutorial. You should come, Jay. Sit in the chat.
It sounds very exciting, actually. That would be awesome.
Okay. Well, it'll probably be next Thursday. We'll see.
Okay.
All right.
Alrighty.
Mr. Coop, I'm glad you liked it. Come back again.
See you later, Eugene.
All right.
See
Bye,
you
Jay.
later.
Bye, everybody. Thanks for coming.
Yes, thank you.